Today, we are tracking what has to be one of the absolute wildest trajectories in tech history. We're going to follow this incredibly cinematic journey of a scrappy 1990s startup that just wanted to make video games look a little better, and see how they morphed into a $3 trillion empire that is literally building the engines of the AI revolution. It's a story packed with near collapse, visionary bets, and a total transformation of how computers actually think. To really get how we arrived at today's AI boom, we actually need to rewind to 1993. The World Wide Web has just opened to the public, and three engineers, Jensen Huang, Chris Malachowski, and Curtis Preem, are sitting in a Denny's diner on Berryessa Road in East San Jose, literally sketching out a company on paper napkins. They definitely weren't trying to build AI. They just realized that computers back then were terrible at rendering visuals, because everything had to be calculated by the main processor, one task at a time. Their singular mission? Make gaming graphics fast. And their seed capital? Just $40,000. I mean, think about that for a second. When you compare that tiny sum to the incomprehensible scale of the modern AI industry they'd eventually trigger, it's almost hard to believe. But they took that money, combined their microchip expertise, and set out to build dedicated hardware to offload parallel processing from the CPU. Part 1. 30 days from bankruptcy. So the rise to the top? Yeah, it was anything but smooth. By 1996, a bad bet on their early architecture almost completely wiped them off the map. Their first major product, the NV1, was a total commercial failure. By the time they were working on their follow-up, the Riva 128, they literally only had enough cash left for 1 month's payroll. Jensen Huang actually started opening internal presentations with a stark warning: our company is 30 days from going out of business. And that wasn't just a dramatic hook. It became a permanent part of their corporate DNA, driving this relentless, almost paranoid focus on survival and rapid iteration. The real defining moment of this whole near-death era was the Sega crisis. NVIDIA was on the hook to build a chip for the Sega Dreamcast, but Huang realized their architecture was a complete dead end. It just wouldn't scale. So in a massive gamble, he goes to Sega's CEO, Shoichiro Irimajiri, admits they built the wrong architecture, and boldly, honestly audaciously, asks Sega to pay them for the contract anyway, for a product Sega would never even use. Miraculously, Irimajiri saw their potential and actually secured a $5 million investment. That lifeline let NVIDIA slash their workforce, pivot hard, and survive just long enough to rebuild. Part 2. Inventing the GPU. That incredibly painful pivot forced NVIDIA to align with industry standards, and it set the stage for a breakthrough that would alter computing forever. In August 1999, they dropped the GeForce 256, and they didn't just call it a graphics card. They boldly branded it as the world's first GPU, or graphics processing unit. By cramming all these complex rendering engines onto a single chip, they fundamentally broke the mold. They completely removed the heavy visual rendering load from the host CPU. If you want to visualize this paradigm shift, think of your CPU as a single, wildly fast worker who tackles one really complex task at a time, sequentially. A GPU, though, it's like an entire army of specialized workers. It uses a parallel architecture to crunch millions of tiny tasks all at the exact same time. If you're trying to render a 3D world with thousands of dynamic pixels and shadows, you don't need one fast worker. You need the army. This new chip could process a minimum of 10 million polygons per second. It was an absolute massive leap in 3D gaming performance, and gamers ate it up. The hardware just kept improving year after year, and for the next decade, NVIDIA was the undisputed king of the gaming hardware world. Part 3. The billion-dollar CUDA gamble. But here's where things get really fascinating. Jensen Huang saw that the GPU wasn't just for pushing pixels, it was actually a general-purpose parallel computing engine. And that realization led to the most dangerous and visionary pivot in the company's entire history. In 2006, NVIDIA made a highly unpopular move. They released a software programming platform called CUDA. Before this, if scientists wanted to use GPUs for heavy math, they had to write their code to literally look like graphics operations. It was a total nightmare. CUDA meant anyone could tap directly into that parallel processing power using standard C-based programming. The only problem? Absolutely nobody cared. Building CUDA roughly doubled the manufacturing costs of NVIDIA's chips because they had to add new physical logic just for this software layer. They essentially handed the world a supercomputer, and the world just stared back blankly. Wall Street's reaction was swift and brutal. Analysts were openly asking if Huang had completely lost his mind. I mean, why is a video game hardware company sinking billions into scientific computing? The backlash was so severe that NVIDIA's valuation cratered, plummeting from roughly $12 billion down to just $2.5 billion. But NVIDIA just refused to back down. They kept quietly baking CUDA into every single consumer graphics card they shipped, and over the years, this built an absolute fortress of an invisible moat. Millions of gamers were buying these cards to play games, but they were secretly buying mini supercomputers, essentially subsidizing the massive R&D costs of building an AI ecosystem. By the time researchers finally woke up and realized they desperately needed parallel compute, NVIDIA's platform was literally already sitting on their desks, ready to go. Part 4. The AlexNet AI Big Bang. It actually took a full 6 years for the academic world to catch up and validate this massive gamble. The year is 2012. There's this somewhat obscure academic competition called ImageNet, where researchers try to build software that can accurately classify over 1 million photographs. Up to this point, AI research was mostly stuck running on traditional CPUs, with scientists trying to hand code strict rules for machines to follow. Well, everything flips when a team from the University of Toronto, led by Geoffrey Hinton, brings in a deep convolutional neural network called AlexNet. They realized something crucial. The parallel nature of neural networks is basically a perfect match for the parallel architecture of GPUs. So they trained AlexNet using 2 standard NVIDIA GTX 580 gaming cards running CUDA. And the result? It completely changed the world. AlexNet hit an error rate of just 15.3%. It absolutely crushed the second-place entry by more than 10 full percentage points. A gap that huge silenced the skeptics overnight. The entire tech industry suddenly realized that deep learning actually works. If you have the right hardware, boom. Google, Amazon, Microsoft, Facebook, they all pivot immediately, kicking off the modern AI gold rush. And every single one of them needed NVIDIA GPUs to do it. Part 5. Building the AI factory. Fast forward to right now, and we've completely shifted from rendering game textures to building out the staggering economics of modern AI infrastructure. The demand is just off the charts. We've hit what Jensen Huang calls the inference inflection point. AI has moved from just training models in a lab to running them live, in real time, for millions of users. The compute demand per token has exploded roughly 10,000 times over in just the last 2 years alone. To meet that insane demand, NVIDIA's engineering response has been nothing short of staggering. Their Hopper architecture, specifically the H100 chip, was the 80 billion transistor workhorse that basically kicked off the whole ChatGPT era. But their new Blackwell B200 chip, it makes the H100 look kind of small. With a mind-bending 208 billion transistors, Blackwell pushes peak performance from 2,000 up to 5,000 teraflops. It's radically changing what data centers are capable of. But, as performance scales up, the economics shift right along with it. On the B200, high bandwidth memory, or HBM, now makes up roughly 45% of the hardware's manufacturing cost. We're witnessing a permanent structural shift in the industry where the memory required to feed these massive language models is becoming just as critical and nearly as expensive as the actual processing logic itself. And the market has responded to this whole shift with a mind-blowing influx of capital. NVIDIA is currently projecting at least $1 trillion in committed data center demand by the year 2027. We're seeing entire nations stepping up and treating AI compute as critical sovereign infrastructure, right up there with electricity or the power grid. It's just an unbelievable evolution, right? A company sketched out in a Denny's diner, pushed to the brink of bankruptcy multiple times, somehow manages to use video game graphics to fund an invisible moat that's now powering the next industrial revolution. As we step back and look at the immense scale of Blackwell and whatever comes next, it leaves us with a truly provocative question. Despite the trillion-dollar factories and these massive technological leaps, are we actually still just in the early days of parallel computing? Thanks so much for joining us for this explainer. Catch you next time.